Hello students, so welcome to Pravegaa Education, and I am here solving one very beautiful problem and very insightful problem from IE Irodov. So you know that Irodov is one of the very fundamental problem books, and there are a lot of very insightful problems. So everybody should solve this one. So this is very important for every category. So you can just choose any problem and you have to solve according to your need. So let us try to go for this problem. This is very interesting one. And this is a problem number 1.63. So this is mainly problem from the general physics. And what is this problem? So straightforward, I am just going to this particular picture. So I will solve it. So there is a two mass and they are sliding, one mass is sliding on a pulley and another mass is just go up and down as the another mass go up and down. So what do you have to do? There is a frictional force between the wedge and this mass m1 and this wedge is not going to move. So what we have to do? We have to find the ratio between m2 and m1 such that the mass m1 will go down or mass m2 will go down and mass m2 will go up and it will remain rest. So there are three questions we have to solve. So once we will solve first two, then third will be very obvious. Only we have to do some analysis. And yes, coefficient of friction is given k and the angle of inclination is alpha. So let us try to solve this problem from scratch. And when you are solving the Irodov problem, you have to always keep in mind that problem will be little bit lengthy. So you have to spend time, step by step you have to solve the problem, and most of the question you have to solve with the first principle, such that you can just enhance your concept. Let us try to go for this. So what I have this kind of situation. This is my wedge. This angle is alpha. There is particle m1 and there is another block that is m2. So this is your m2. So case 1, the problem number 1 is m2 will go downward. So m2 will go downward, that means m1 will go upward. That is the thing. So when m2 will go downward, that for the m2, if downward force is more than upward force, then it is going to be downward. So for m2, what is my free body diagram? So I am just going for the free body diagram for m2. So this only force is m2g and tension will be this one. So only these two forces are there. So what will happen? m2g must be greater than tension. Then only it is going to down. Now, what is condition on m1? So when we are going for the m1, then this is my particle, this is my angle alpha. We have weight, that value is equal to m1g. One component of weight is equal to m1g sine alpha, and another component, another part is the tension. So this is your tension, and this value is equal to m1g cos alpha, because we know this angle is alpha, and there is a normal. Now the whole thing is, what is the direction of frictional force? So if m2 will go downward, that means m1 must go upward. That means if m1 will go upward, that means frictional force will in downward direction. So what will happen? For this particular thing, we can write tension must be greater than m1g sine alpha plus frictional force. And what will be your frictional force? So hence there is not any motion in a vertical direction. So obviously normal force must be equal to N must be equal to mg cos alpha. mg cos alpha. So I can write my this tension must be greater than m1g sine alpha plus k m1g cos alpha. So this is condition. Now you can combine these two things because we have to just talk about the ratio between M2 and M1. So this is my first equation. This is my second equation. M2G is greater than T and T is greater than this one. So you know if A is greater than B and B is greater than C, then A is always greater than C. So from here we have M2G must be greater than M1G sin alpha plus K M1G cos alpha. And from there we can write M2 upon M1 must be greater than sin alpha plus K cos alpha. So this is the condition where the particle M2 will go downward and in another way M1 will go upward. So this is the problem number 1. So it's 1.63a. Let's try to go for, in the same way, we will just go for M2 will go up. Then what is going to happen? So let us try to go for this one. So case 2 or problem number B, M2 will go up. If M2 will go up, that means M1 will go down. M1 will go down. Then again we will go for this whole condition. So this is my alpha, so not theta. So I am just making. So what will be case for the M2? For the M2G is there and now tension is there. Now it is going upward. So that means tension is greater than M2G. So it is going upward. So if it is going upward, then the second particle M1 must go downward. So we have this value is equal to M1G. This angle is alpha. This value is equal to M1G cos alpha. There is a normal and this value is equal to M1G sin alpha. So if it is going downward and tension is always there, so these forces will remain same. Only one force that is going to change its direction is the frictional force. So why we are saying frictional force at the self-adjusting force? So why? So this is the direction of frictional force. So what will happen? If it is going downward, that means M1G sin alpha minus frictional force, because frictional force have this direction, must be greater than tension. Then only it is going downward. And yes, again I can write M1G sin alpha minus frictional force. So that is K M1G cos alpha must be greater than tension. And again you have tension is greater than M2G and this one is greater than tension. So this is greater than tension and tension is greater than M2G. So you have M1G sin alpha minus K M1G cos alpha must be greater than M2G. So what will happen? We have G sin alpha minus K, and G can be also cancelled out on both sides. So sin alpha minus K cos alpha must be greater than M2 by M1. So this is your problem number B. And now for the problem number C, we need nothing to solve, only we have to analyze these two things. So let us try to go for our next part. So what we have, if I have sin alpha minus K cos alpha is greater than M2 by M1, then what is happen? Then M2 will go upward. And when we have M2 upon M1 is, that is into the last to last slide, when M2 upon M1 is greater than this one, so this will be greater than this one. So that value is greater than sin alpha plus K cos alpha. Then M2 will go downward. So this is the scenario for which your particle will move. If you have this type of ratio, then particle will go either M1, either up or down. What we have to do, we have to make a scenario for the problem number C such that neither it will go up, and neither M2 will go up, neither it will go down. So we have to discard this one. So we have M2 upon M1 here, and hence this is greater than this one. So we have this scenario, sin alpha minus k cos alpha minus k cos alpha, that is M2 by M1 must be greater than this one. Then my particle will stop, or this must be less than this one. So that value is equal to sin alpha plus k cos alpha. So here we can take the equality sign also, such that we can go for the limiting case. So for this particular case, the particle, so this is the reverse of this condition, this is the reverse of this condition also. So if both condition is going to reverse, so particle is neither go upward nor go down. So it's a wonderful problem to understand the self-adjusting nature of friction and what is the condition where your particle will move or not going to move. In general, when we see the pulley question, we just start to solving equation of motion. You have to solve the equation of motion when there is a perfect condition is given. And if there is friction, it should be given that whether it is moving downward or it is moving upward. And here we need not to find the acceleration of a system. Here we have to just find the ratio of M2 by M1. So this is very applicable also. So onto that particular ratio, M2 by M1, we can check whether it is moving up or down. So students, you can solve this problem with yourself, and you can also demand that which problem we have to solve next, such that you can be benefited with this particular series of IE Irodov by the team of Pravegaa. Thank you.